So remember, what we're going to do is we're going to talk about reactions for the preparation of alcohols. And where we're going to start is with these hydration of alkene reactions. Alkenes undergo addition reactions. Hydration is when you're adding water to that alkene. And really what you're doing is adding a hydrogen from water to one side and the OH from water to the other side, thus creating your alcohol product. All right. These reactions are, from a free energy standpoint, favorable reactions, but they do have quite the activation energy barrier to overcome. So if you take an alkene and you mix it with water, you're going to have to wait 1,000,000 years to get this hydration reaction to occur. So there's always going to be some catalyst in our set of reagents that are going to help catalyze this reaction. Okay? Cool. So we're going to have different sets of reagents for these hydration reactions. The first one we're going to look at is sort of the simplest of them, what is called the acid catalyzed hydration reaction. All right, importantly, this one right here, we can just make a note, is one that we're going to have to know the mechanism for. So we're going to take a look at our mechanism for this reaction. Okay, so let's just take an example here. We're going to take an alkene. And we're going to mix it into a solution of concentrated sulfuric acid. And we're going to heat it up. Psych, we're not going to heat it up. That's for the other direction. All right. Importantly, our double bond here, we would get a different product depending on which side we added this to. For our acid catalyzed hydration reaction, these reactions prefer the more substituted carbon. So we will specifically have that hydroxyl group added to the red carbon and my hydrogen added to the other side, added to the blue carbon. Okay, these reactions that had this sort of more substituted carbon regioselectivity we called Markovnikov. Clearly named after some Russian dude. All right, and so this reaction would be considered a more Markovnikov reaction, a reaction that favors that more substituted carbon. Okay, so like we said, we got to know our mechanism here. All right, we'll take our same reactant. All right, and this idea of being acid catalyzed implies that we have hydronium ions, and these are going to be active in our reaction mechanism here. Okay, so we're going to have our acid. I'm going to kind of write it in this specific way here. where I'm explicitly showing one of those hydrogen-oxygen bonds. You can draw the full Lewis structure. All right, this is kind of the lazy man's way to do it here. All right, and what happens is that pi bond pair of electrons is going to reach out and grab that acidic proton. All right, so in this reaction here, what is it that is playing the role of the nucleophile? Is it the alkene or the hydronium? The alkene, right? Specifically, that pi bond in our alkene is our nucleophile. That's that electron-rich species. That bond itself, that pi bond, is our nucleophile. And that acidic hydrogen is our electrophilic site. Okay, so everybody take a second. Draw me the intermediate of this reaction here. So, really we could have drawn two, because we can either add our hydrogen to the red carbon or to the blue carbon, right? Could be on either side of our double bond. But if I add my hydrogen to one side, what necessarily has to go on the other side? Yes, but even before that, in my intermediate step here, what's missing are charges. I don't have my correct charges on these intermediates here, right? This other carbon, if we just kind of want to imagine real quick, let's take this alkene. Here's my water, and I have this pi bond pair of electrons right here. Well, when that pair of electrons reaches out and grabs that hydrogen, I snatched it away from that carbon right there that used to have a complete octet. I took its electrons away from it. So remember, our intermediates here are going to be carbocation intermediates. One of those carbons is going to get a hydrogen, the other one's going to be left with an incomplete octet and get a positive charge. Okay? You can convince yourself of this as well by filling in all the implied hydrogens, right? This blue carbon has one, this red carbon only has two. If I add an extra hydrogen to that blue carbon, it's got a full octet. But now my red carbon is only left with 3 bonds, right? So if you fill in those implied hydrogens, it might be easier to see this phenomena as well. Again, I kind of think of it as that pair of that carbon got that pair of electrons taken away from it, right, when this reaction occurred. Okay, only one of these two intermediates are actually going to form. Which one? The one on the left or the one on the right? Yep, the one on the right. This guy right here is bad because we don't like primary carbocations. So we said that this reaction was a Markov-Nikov reaction. That is because of this mechanism right here, because of our carbocation mechanism. All right, so I will tell you there are 2 more steps in this mechanism here. We're now going to react our carbocation with water. All right, I want you to take a second and see if you can't get from A to B on this one. We know what our product is. See if you can't fill in those last 2 missing steps. rather that last, put in your electron pushing arrows, and fill in this intermediate here. Alright, so one of our goals for this unit, and really for the remainder of this course, is to really try to understand these reaction mechanisms, right? And when they're first sort of introduced, I think a lot of students treat them as memorization sort of things. Like, I just need to memorize what this mechanism is for this particular reaction. That works great when you got one or two of them, right? At some point, you're going to reach like a critical mass in your brain where you're not going to be able to memorize every single reaction mechanism. You want to really sort of understand what's going on so that you can fill in the gaps by doing sort of reasonable moves, all right? And it is sort of some guess and check where you're like, all right, let's try this. Okay, that didn't really work. But being able to follow these arrows are really important here, okay? So I need to create a new bond between carbon and oxygen, right? If I just play the spot the difference game between where we're going here, I need to create a new bond between that carbon and that oxygen, okay? So let's think. I'm going to make two copies here. I want you to tell me which one's correct. I'm going to do a bond formation arrow from my carbon to my oxygen. Which one of these two is correct? Should the head of the arrow be pointed at the oxygen, or should the head of the arrow be pointed at that carbocation? Everybody take a second. Which one of these would be the correct step in our mechanism, left or right? All right, let's take a vote. Who thinks it's left? Who thinks it's right? Wonderful. We got to start the base of that arrow at a pair of electrons. That carbocation does not have a pair of electrons, right? We can also think about it. Our base of our arrow has to be at our nucleophile. Carbocations are electrophiles. So absolutely, that's going to be this one right here. Okay, so the water's carbon is going to come down and form a new bond here. That means this pair of electrons is going to go from being a lone pair to a bonding pair. All right, so that lone pair is now this new bond. So my oxygen has now only one lone pair. And how many hydrogens does it have? 2. So what else do I need to include on this intermediate here when an oxygen has 3 bonds and 1 lone pair? That charge. Okay? So I'm close. I'm so close, but I'm not quite there yet, right? I have my hydroxyl group OH, and here I have OH2. All right, so the last step is I need to deprotonate this positively charged oxygen here. That would be a proton transfer step. All right, so what we need is a base to accept that proton. Okay? What we don't do in our mechanisms in organic chemistry is just kind of let those hydrogens go flying off into space. All right? Something has to accept that proton. Okay? And importantly, when we have an acidic conditions here, our acid is that hydronium ion, but oftentimes we also need a base, right? Just like in this case here, we need something to accept protons. That happens all the time in mechanisms. Under acidic conditions, importantly, your base can't be like your go-to default base that you think of in your brain, hydroxide. This would never survive under acidic conditions. It's just going to react immediately and disappear. So for our acidic condition reactions, our base is going to be water. All right, your acid is hydronium, your base is water. Okay, so what's going to accept this proton here is going to be a water molecule. All right, and now you have a nice, beautiful reaction mechanism, because not only did you get to your product, but you also reformed your acid catalyst at the end. And remember, what it means to be a catalyst is that it's not consumed in this reaction, right? So we have a mechanism that shows that yes, we sort of use this acid, this hydronium ion, but we also make it again at the end. So it's not actually consumed in our reaction. What is consumed is that water molecule, right? That's what's being added to our alkene. All right, so our acid catalyzed hydration is a carbocation mechanism, which is why we see that Markovnikov regioselectivity in this reaction. Okay? It's also a cautionary tale in terms of what can happen or what can kind of go awry when we carry out these reactions. What do we always have to watch out for with carbocation mechanisms? The shifts, right? So carbocation, we're just going to, carbocation mechanism, and so we're going to make a special note. Watch out for shifts. And this is indeed sort of the downside of this particular method here. It's sulfuric acid is like the cheapest thing that you can have in an organic chemistry lab. You got your DI water, right? So if you're trying to do a hydration reaction with minimal cost, this is definitely the way to do it. All right, the downside is those carbocation rearrangements, right? These side reactions that aren't necessarily what you're expecting to have happen, okay? So if you do have this reactant that you're really worried about it undergoing any sort of hydride shift, we would use another method instead, all right? So this is what's called a oxymercuration. We'll take our same alkene here. All right, and what we're going to use is what's called mercury acetate, HgOAc 2 in water. So this mercury acetate is going to help catalyze the addition of this water molecule in this reaction. Okay? In order to kind of break down this catalyst that you create, this intermediate, you have a second step where you follow it up with this reducing agent, sodium borohydride. This reaction here, again, is what you would do if you were trying to do the acid catalyze, but you couldn't because you had to worry about shifts. So it also is the Markovnikov addition of water, where you get the OH group on the more substituted and the hydrogen on the less substituted. in our previous hydration reaction, we saw the mechanism, right? So we were able to show that it was Markovnikov and that we had to worry about shifts. In this one, you're just going to trust me here. All right, for this one, we have no mechanism. There are just sort of two things that we're going to note about this mechanism, even though we don't know what it is. And that is that, first of all, it's Markovnikov, as we established. All right, but then also, it's not a carbocation, so there are no shifts to worry about here. So with this particular method, you would have no shifts to watch out for. There's one more hydration of alkene reaction, what's called a hydroboronation. All right, let's take our same alkene. You're going to react it with what's called borane, BH3. All right. You'll see it usually presented in our textbook. This is how it is, so I'm going to be consistent here. Tells you the solvent that it is in. These reactions are carried out in tetrahydrofuran, a particular solvent. All right, and then you follow it up with peroxide and sodium hydroxide, peroxide and base. Okay, now the claim to fame of these hydroboronation reactions is that boron as a catalyst kind of orients this molecule in such a way that you get the hydroxyl group on the less substituted carbon and the hydrogen on the more substituted carbon. All right. Again, we have no mechanism for this reaction, but we're going to note that it's anti-Markovnikov. All right. Again, we get the hydroxyl group on the less, not the more substituted carbon. And fortunately, we also have no shifts to worry about. Okay, so we get this anti-Markovnikov hydration of our alkenes. So now we have a method to put that hydroxyl group on the less substituted carbon. Okay. Again, it has to do with this complex between borane and your alkene. Your textbook has a pretty nice little diagram. I'm just going to note it's anti-Markovnikov. That's what we need to know. Cool. All right, so let's just summarize these hydration reactions real quick. All right, we're going to take an alkene and we're going to make a little reaction wheel using our 3 hydration reagents here. Okay, we'll take our sulfuric acid solution. Do our oxymercuration. So everybody take a second, just sort of put them all next to each other and summarize, fill in this reaction wheel. Great little study tool for summarizing reactions. All right, so for our oxymercuration reaction, this one puts the hydroxyl group on the more substituted carbon, whereas my hydroboronation reaction puts the hydroxyl group on the less substituted carbon. Okay? My acid catalyzed hydration reaction favors that more substituted carbon, but I also got to watch out for what? Those shifts. And in this case, I have that more substituted carbon next door to my carbocation, and so I will indeed see a shift, placing that on that more substituted carbon. Okay, so really pick this example to make a point here to highlight the differences between these reactions here. We got Markovnikov for our oxymercuration, anti-Markovnikov for our hydroboronation, and our acid catalyzed is Markovnikov. But we gotta watch out for shifts. Cool. All right, so we're gonna introduce a new reaction for preparing alcohols here. These are what are called Grignard reactions. Have you ever talked about these? Sometimes, every once in a while, they're introduced kind of early. They do kind of play a little bit of an outsized role in organic chemistry, and that's because they work really freaking well, right? And they're not very expensive reagent-wise. They're just sort of great reactions that create alcohols, but importantly, they also create new carbon-carbon bonds, all right? And this is going to be one of these things that makes these reactions a little bit scary, is we're not just like swapping out an OH and a chlorine or something, right? We're actually making a bigger, uglier molecule on our product side. Counting carbons is going to be especially important for these reactions here, all right? So again, our Grignards, we're just gonna make a note. These create new carbon-carbon bonds. so a Grignard reaction will require what's called a Grignard reagent. And this is one of the most magical reactions I've ever seen. It still kind of blows my mind, but it turns out that if you take an alkyl bromide, something that's just relatively easy to prepare, right? And you mix this with solid magnesium, magnesium metal. Okay, you just take little shavings of magnesium. You can buy them in little ribbons, cut them up, throw them in with your alkyl bromide. That magnesium will magically work its way between the carbon and the halogen, and you get this Grignard reagent here. My magnesium has inserted itself between the carbon and the bromine in this compound. All right, and this is what we call a Grignard reagent. All right. This is what's called an organometallic reagent. All right, what do we think organo means? Organic, right? Because it's got those carbon and hydrogens. But metallic because it has this metal in here, right? And so looking at this Grignard reagent here should really kind of irritate your organic chemistry brain, because what I just drew here is a covalent bond between this carbon and this metal magnesium, right? This is not something that we expect to happen. So again, magic, how the hell, all right? But that is exactly what we're seeing here, is a covalent bond between this carbon and this magnesium. And that is what's going to make these Grignard reagents so useful, okay, is because carbon we really don't think about as a very electronegative element, because we're always comparing it to its neighbors, to nitrogen, to oxygen, to the halogens, all of which are way more electronegative than carbon, right? So in terms of the non-metals, we really think of carbon as being on the lower end of the electronegativity scale. But compared to a metal, compared to a group 2 metal, this thing is like ridiculously electronegative in comparison. So in this bond right here, what we see is a huge amount of partial negative charge sitting on that carbon atom, and a huge amount of partial positive charge sitting on that magnesium. All right, some places, some textbooks will even go as far as to tell you to think of it as an ionic bond between these two, between a carbanion and this positively charged magnesium. All right, the bottom line is whichever kind of mental picture you have, this carbon atom right here has a huge amount of electron density. All right, and what do we call that species with a large amount of electron density in our chemical reactions? The things that like to react with stuff that doesn't have a lot of electrons, right? What's the one that has a lot of electrons, the nucleophile or the electrophile? The nucleophile. So our Grignard reagents right here, we've created a carbon with a butt ton of electron density, which means we've just created this nucleophilic carbon, all right? So a Grignard reagent, carbon has a lot of electron density, all right? The punchline here is we have a nucleophilic carbon atom. By taking that alkyl bromide and mixing it in with that magnesium shavings, we've created this carbon nucleophile we call a Grignard reagent. Okay? This particular Grignard reagent, well, not this particular one, Grignard reagents will come up quite a bit throughout the remainder of this course. We're going to introduce it with a bunch of new functional groups. All right? For right now, our focus is the creating of alcohols. So what we're going to work on are these reactions. Again, Grignard reactions. All right, but specifically those that convert aldehydes or ketones into alcohols. All right. We will sort of exclusively focus on aldehydes and ketones later in the course. But for right now, what we need to know about our aldehydes or ketones, let's get an example down. All right, now let's look at this carbonyl bond here, and let's think of the polarity of this bond. Where's the electron density in this bond? All right, oxygen is the more electronegative atom, so it has a lot of electron density, leaving that carbon with this relative lack of electron density. All right, so ketones and aldehydes, that carbonyl carbon is electrophilic. All right, that can be ingrained into your brain right now. You will have a super time in future chapters. Electrophilic, carbonyl carbon. You're going to hear me say it a bajillion times throughout the course of this course, all right? Throughout the remainder of this course. Our carbonyl carbons play the role of electrophiles. All right, and so what we're going to do is we're going to take this and we're going to react it with our Grignard reagent. All right, and again, our Grignard reagent is our nucleophile. Okay. Specifically, right, we said it was this carbon right here. So I want to do my mechanism for these Grignard reactions. Grignard reactions we need to know our mechanism for. I actually think that the mechanism here, thinking about the mechanism, is helpful in figuring out what your products are. All right? Now, if I'm going to do my, all right, I know nucleophiles attack electrophiles, right? I can't do, whoops. I can't do this. What's wrong with this? So, two things, absolutely. One, that carbon at the top has too many bonds. But two, and very importantly, the base of my arrow has to start at a pair of electrons. It can't start at a carbon atom. All right, so the pair of electrons that is going to be involved in this reaction is that magnesium carbon bond, right? That pair of electrons that's being shared between that superpolar bond where all that electron density is sitting on that carbon atom is that covalent bond. That's the pair of electrons that's going to be involved in this step in my mechanism. That's my nucleophile attacks electrophile. Okay? Now, absolutely. So now we had another problem, which is I can't stop there because my carbon atom, that's my carbonyl group, would have too many electrons, all right? So what we're going to see as a pattern in our mechanisms with these electrophilic carbonyl carbons, one of the reasons that they're such great electrophiles is they're really good at accepting pairs of electrons because they can kick this bond onto that more electronegative oxygen atom. right? That makes them very easily able to accept a pair of electrons without ever breaking their octet, right? They just kind of transfer that electron density up onto that oxygen atom. Okay, so everybody take a second. Draw me my intermediate in this reaction here. I'm going to tell you at this point the magnesium bromide thing just kind of goes off into the solution. No longer attached to that molecule, right? So we need to make our new, put these things together compound here. So everybody take a second, see if you can't draw out our new compound. I guess to be clear, this arrow right here is what? Bond breaking, bond formation, right? We're making a new bond between that carbonyl, I guess we're breaking this bond as well, but importantly, we're making a new bond between those two carbon atoms. All right, so let's start out here. We need to connect these 1, 2, 3, 4, 5 carbons from my ketone to these 1, 2, 3, 4 carbons from my nucleophile. And importantly, I'm going to need to connect to this new bond carbon right here, my formerly carbonyl carbon. Okay, so first of all, it has that oxygen on there. All right, now this pair of electrons that I moved with my electron pushing arrows, they were a pi bond. Now what are they going to be in my intermediate? A lone pair. So that pi bond pair of electrons, what I did with that arrow is I grabbed them and I moved them up onto that oxygen atom. So now I have this lone pair over here. That was my pi bond. Now it's a lone pair. And if this oxygen has 1 bond and 3 lone pairs, what should its formal charge be? Negative. Okay? Let me move this guy here over here. Cool. So now I need to make my new carbon-carbon bond. Right? Like we said, these reactions are going to form a new carbon-carbon bond, which means on the other side of this new bond is that blue carbon, the one that used to be attached to my magnesium. And now I just have to make sure to attach everything else. It was attached to another 1, 2, 3 carbons. So 1, 2, 3 carbons. What's up?
Would it go through shifts at all?
These are not a shift thing because there's no carbocation. All right. So now let's just do our sort of ultimate double check and counter carbons, right? We should have had 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, added to another 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, all right? So just kind of following who's who from the reactant side to our product side. Again, that oxygen has accepted another lone pair, so it's going to have this negative charge. All right, and then I've connected these two molecules. I connected the carbon that was bound to the magnesium in my Grignard to my carbonyl carbon in my aldehyde or ketone. All right, we see that what we're left with here is not quite an alcohol yet. All right, and that's because there's always this second step in your Grignard reaction. Your Grignard reactions, you first create these intermediates here, or I guess these negatively charged alkoxide ions is what they're called, and then you protonate them by just adding in some dilute acid. All right, so our last step here, I guess I can do it in my mechanism, I'll be good and sort of show. We have H plus, that lone pair on the oxygen is going to reach out and grab that hydrogen and become protonated. So at the end of the day, we have this tertiary alcohol, and we've created these new, added on these new 4 carbons to my existing 5 carbons. All right, and again, what's going to make these reactions kind of scary is the fact that we got this big, ugly product. We grew our carbon chain here. All right, but nonetheless, if we follow our process, it's not too bad. Let's just do one more example here. All right, so how you'll see your reagents written in your reaction is step 1, use that Grignard reagent. And step 2, follow it up with that dilute acid. What do they call that? They call this, you'll hear this called the acidic workup step. One of the great things about these Grignard reagents, again, they kind of play an important role, an outsized role, because you can create these new carbon-carbon bonds with such ease, just starting out with an alkyl halide. There's also like no restrictions on what that alkyl halide can be. You can pretty much start with anything, including something with a benzene ring, right? There's no limitations on it being a ring or sp2 hybridized or any of that jazz like we run into sometimes. So again, just another reason why these ones are so popular. All right, oh geez, sorry. To be clear, we're going to need to connect the carbonyl carbon in our aldehyde to the carbon that's at the base of that magnesium, bound to that magnesium. So when I'm going to draw my products, I'm going to start out with those 3 carbons, and I'm going to say, all right, you're my carbonyl carbon. All right, just like over here. Whoops. So then I have my oxygen, but now it's only single bonded, and I got my new carbon-carbon bond. When I draw that new bond, I know automatically who lives on the other side of that bond. It's got to be that blue carbon. So then I just attach everything that blue carbon had around it, which in this case was that benzene ring. All right, and then when I do my acidic workup, that step is what protonates that oxygen, giving me a hydroxyl group, giving me an alcohol. What's up?
And obviously it doesn't matter here, but if the benzene ring had another substituent on it, it would for sure have to be in the right spots and everything.
Correct, absolutely, yeah. There's no moving around or anything that would happen. You're just literally picking this thing up at its blue carbon and attaching it to that carbonyl carbon. Yep. Cool, so starting with an aldehyde, you can see that now we've also created an alcohol here with our new carbon-carbon bond. Wonderful. All right, cool. We will continue. This is a bit of a longer chapter than previously, so we're going to continue with our discussion of alcohols next week. Up until this point, we've talked about reactions that make them, right? We'll talk about other reactions of alcohols starting next week.